Hello, hello. All right. We are 2 minutes behind, so it's time to start, I think. Some people will come in, hopefully. Uh, I'm very excited to present George Konidaris, Professor George Konidaris, who is an associate professor of computer science and the director of the Intelligent Robot Lab at Brown, which forms part of the Big AI Brown Integrative General AI. His research is driven by the overarching scientific goal of understanding the fundamental computational processes that generate intelligence and using them to design a generally intelligent robot. And Dr. Konidaris is also a co-founder of two startups, Real-Time Robotics and Lelipa. Is this the right?
Lalapa.
Lelapa AI, sorry. Want to make sure I don't butcher it. And hopefully we'll hear a little bit about them also. Help me welcome George.
Thank you. Thanks very much. It's a great pleasure to be here. Usually I talk about a lot of stuff, but since it's a task and motion planning workshop, I'm going to focus a little bit. Oh, you need me to be louder? Sorry, I'm speaking into the microphone. I feel like Celine Dion. This is okay? At the back? Good, great. All right. So let's talk about task and motion planning. As you all know, our sort of kind of mental framework that we all have in our head for task and motion planning is that at some high level there is going to be an abstract, discrete task representation, and at some low level there's going to be like the robot actually interacting with the world. And in my lab we call the low level swampy and the high level crispy. And task and motion planning is all about reconciling plans found at the crispy level with those at the swampy level. What I want to talk about mostly today is where does that crispy level come from, and what exactly should it mean? Okay, it's not given, right? It's not a thing that comes with your robot. Your interaction space, your low-level sensorimotor control is a thing that comes with your robot, but the high-level crispy space is fictional, right? You get to hallucinate it. You can make it up to be whatever you want in order to support effective planning. And so the question is, how should it be designed? And I think that this question is really just about as fundamental a question in all of AI as there exists. And let me tell you about why I think that for just a second. When you are building a narrow intelligence, when you are building a robot or an agent that solves one single task, you get to design the input and output channels of that agent. Okay, so if you're doing something that plays Go, you get to decide that your set of states or your set of inputs are the legal Go boards and your actions are legal Go moves. And if you're just building something that detects illness in an X-ray, you get to decide that your inputs are X-rays and your outputs are illness or no illness. And if you're doing a language system, you get to decide that your inputs are text sentences and your outputs are like, a question or a yes or a no. Okay, but you can only do that when you're building a narrow intelligence. You can only do that when you're building something that only does one thing. Okay, and that's like a contradiction in terms. There are no narrow intelligences. That's just not a thing, right? Intelligence is intelligence because it's broad. Narrow intelligences are no intelligences at all. And so if you're going to build an agent that is able to do all of these things, one single agent, you have to have a very rich input and output space. Okay? You have to be a robot, essentially. You have to have a very rich connection with the world because it needs to be able to support all those input spaces in a single agent. Okay? And what that means is that you have something that we call the sensorimotor dilemma. The more general your agent is, the much richer its sensory input and output space is going to have to be, the less well-suited it is to any individual problem. All of the rest of AI makes the assumption that this problem has gone away already. All of the rest of AI assumes that you arrive at a task phrased neatly and nicely for your specific input and output specifications for your specific goal. Okay, but that's cheating. All right, so if you wanted to use a robot to learn to play chess, you could assume your inputs are legal chess moves, but that's not actually what is ever going to happen with the general agent. You're always going to start with a really rich input space, and you could try and learn to play chess in that input space. You could try and imagine taking those videos of these really rich scenes and trying to learn which motor you should actuate next and for how long, but that doesn't seem like it's going to work to me. Okay, it seems that the only way that you might be able to do this is you have to take that scene and those motors and produce an abstraction that looks like the way someone in some other subfield of AI would have modeled the problem. And that abstraction's got to be very powerful because all of those three images have to be mapped to the same abstract chess position, right? They're the same game. Okay, so they're not visually similar at all. There's something about the game and about the rules, about how it works, that's core, that you want to be able to capture. And if we aren't able to build robots that can construct those things on their own without human input, we can't get to a generally intelligent agent. It's just not going to be feasible. The rest of AI doesn't make sense. We're never going to be able to apply techniques generated there to our problems produced by robots. Now that seems like a scary and challenging and complex thing to be able to do, but it's actually very well defined. Okay, we start out with something called a decision process. You may have heard of decision processes. That word is usually preceded by Markov. That's a special type of decision process. But all a decision process is an observation space, an action space, and a preference function over what happens over traces over those observations and actions. Okay. So if we want to go from this observation space that captures all the complexity of the robot, and we want to get to a different decision process that captures the complexity of this specific task expressed by your reward or preference function, all you need to be able to do is you need to be able to build abstract actions, which we call skills in robotics, and abstract observations, which we often call symbolic representations in robotics. Those two things need to be compatible. They need to be mutually compatible. But if a robot can build those two things, then it can get to a wholly new decision process, which captures the complexity of the task, not the robot. That's how you resolve the sensorimotor dilemma. That's how you deal with the fact that your robot's input and output spaces have to be wildly overpowered compared to the tasks they're supposed to solve. And so what you would get if you can have a robot that does that is you might imagine a robot with an extremely rich sensorimotor space, and then you ask it to play chess, and it builds an abstract decision process that captures the complexity of chess by building high-level actions that are like legal chess moves and high-level observations that are like legal chessboards. And then if you wanted to navigate through the world, you might expect that it builds a map, and it builds a graph over that map, and the high-level actions are like walking down the street and turning left or right, and the appropriate matching symbolic representation is a graph. And then if you wanted to get it to learn to play soccer, it might find that the high-level actions are like kicking with a particular force or running in a particular direction, and the high-level observations are continuous. And we might not describe these as symbolic, right? That might not feel symbolic because they're continuous. But the symbolic thing is actually a red herring. The right question is, what is the appropriate maximally compact abstract representation that captures the complexity of that task? Okay. So this is a sort of recipe for general intelligence. A robot with a single, wildly overpowered observation and action space is given a reward function, one at a time for each task, and then it builds a compact representation of that one task, and then it swaps in from its arsenal of generic problem-solving capabilities. For example, an A-star search would work great over here, adversarial search would work well over here we probably need to do policy search. And those are because we fall into specific subclasses of decision processes. But hopefully at the end of this, you understand that this process, building these abstract actions and observations, is the most critical process, and that it has to be done on a task-specific basis. We cannot possibly rely on having those abstract symbolic representations existing for us. Okay, that's not going to work. The robot is going to have to construct them, it's going to have to learn them on the fly for every specific task. Otherwise, you can't get to this happy diagram. Okay, so this is an extremely important task, and how are we going to think about handling it? The approach that my lab has taken now for some years is to say we need to think really hard about what exactly these abstract representations mean. We need to think about the mathematical formalism of them. We need to have a framework that explains why they are, why they mean what we've chosen them to mean, when they should be discrete, when they should be continuous, when they're deterministic, when they're stochastic, and supports the robot autonomously learning them. So our approach we sort of call constructivist, which is to say that we take a bottom-up approach and we think about, what computation is this robot doing? What computation fundamentally must these representations support? And then we're going to build them by constructions that they can formally, provably support those constructions. And the most important question in all of this is, what should abstract symbolic representations or states mean? Okay, what is the grounding for an abstract state? And if you go through the math, and we've gone through the math, what you find is that in real-life environments, if you take an abstract state, which might be like an AND of high-level symbols, or you might ask about the grounding of an individual symbol, The answer is it has to ground to a probability distribution over low-level observations, not a set. It has to look something like this. You might imagine a robot, it takes an action, and then it might land up in a distribution of states at the low level. And then it might take another action and land up in another distribution. This is what's actually happening when you do high-level task planning, is that you're imagining in the future, your sort of uncertainty over what exactly is going to happen to you in the future is represented by these distributions. Okay, so your symbolic representations are actually expressing uncertainty over your future state. They're like belief distributions over your future state. They can't be sets, they have to have real value numbers attached to them, and they're going to do things like overlap with each other, right? So the formal mathematical definition of the grounding of a high-level symbolic representation is that every high-level state has to ground to a distribution over low-level states. Okay, so you can take something like this and you can assign high-level states that correspond to those distributions. Okay. So just to show you that this isn't completely made up, this is just an experiment we did a few years ago when I was still at Duke. This is an environment that we built. You can see that there's a cupboard over there, there's a switch, there's a cooler, and inside this cupboard or this cooler is going to be a green object. You can see the robot holding the green object over there, and in this case, I just hand wrote some skills. So I wrote a skill for moving between the cupboard and the cooler, and I wrote a skill for opening and closing the cooler, and for opening and closing the cupboard, and for turning the switch on and off, and for picking up this object when you can see it. Now, it turns out that there are some environmental constraints here. For example, you need both arms to open and close the cupboard. And when the cupboard's open, it blocks out access to the switch. You can't reach it anymore because it's blocked. Okay. And then when the robot is holding this object, when it's picked it up, it holds it up here. Okay. And then it can't do things like open and close the cooler or the cupboard. Now, you or I could write down a set of abstract states that represents the sort of task level formalism of this problem, but we'd rather have the robot do it. In fact, we'd rather have the robot do it from something that looks like this. Okay, so these are the inputs to the system. The robot's pose in the map, x, y, theta, a voxelization of the entire room. I've just cut out the cooler over here, and then the raw joint values of that robot's arms. And if you take the math that we did, out pops a symbolic representation learning system where you can have this robot execute those motor skills, observe the raw kind of voxels and map poses, and joint locations of the arm, and then take that and transform it into a drastically more compact abstract symbolic representation. Okay, the important thing to note here is, of course, I've hand-built these skills, so we're pausing for now on where the skills come from. The skills involve motion planning. Okay, they're doing motion planning, but for now we're just treating them as a black box. And if you take the data out of the system, what you get is a PDDL representation there at the top, which is a text file, so inarguably symbolic. It's also provably sound and complete. So it is provably the right symbolic representation for planning with those low-level skills, and it has some symbols in them, and you can ask, what is the grounding of those symbols? So I can say, hey, there's a symbol 1 over here. This operator says, if you want to go from, I think it's the cooler to the cupboard, can't quite see, then you need to be in symbol 1, and afterwards you won't be in symbol 1, you'll be in symbol 0. So we can ask, what is the grounding of symbol 1? And we can draw samples from that grounding distribution and visualize them. And it turns out these two symbols only talk about the location in the map. And you can see that symbol 1 places the robot's pose about there. If you remember right, that's where the cupboard is. And symbol 0 places the robot's location about there, looking in this direction. That's where the cooler is. Okay, so this learned symbolic representation says if you want to move from the cupboard to the cooler, then you should be at the cupboard, and afterwards you won't be at the cupboard, you'll be at the cooler, which seems pretty straightforward, except that the robot discovered that distinction on its own from raw pixel data. It built a learned symbolic representation, a text file, using grounded symbols, and then that text file is provably sufficient for planning. Here's another one. If you want to open the cupboard, you need to be standing in front of the cupboard. We know that one already. This symbol 3 is a distribution of the robot's joints. You'll see that the robot's hands are down here, so it's not holding anything, because that means that the arm is free. And then it will say symbol 4 has to be true beforehand, and afterwards will be false, and symbol 5 will be true. And I've clipped the voxel map of the whole thing and just shown you the cupboard, which is where the changes are, and you'll see that drawing samples from that distribution, you will see that a bunch of things are true in that distribution, but the cupboard is always closed. And afterwards, the cupboard is always open. Okay, so this robot has discovered the notion of the cupboard being open or closed because mathematically that's the formulation that you need to be able to do this planning using that set of skills. Right? In some ways, those symbolic representations are implicit already in the skills. They're the symbolic representations that you need to be able to plan with these. And of course, you can throw these groundings away. You can just take this text file and input it to a classical planner. We did that. It takes 4 milliseconds to find a plan. Here is the robot picking an object out of the cooler. You can see it opens the cooler, but then it does not pick the object up, because if it did, it wouldn't be able to open the cupboard because you need both your hands free. So it goes to the cupboard, but then it doesn't open the cupboard because it needs to turn the switch. Opening the cupboard would block the switch. So first it turns the switch, then it opens the cupboard, and then it goes back to pick up the object, which is not surprising. That is what classical planning classically does. It resolves these sorts of things. What's interesting here is that we learned a symbolic representation in which we can do this task level planning really easily. We didn't have to do it at the pixel voxel level, and the robot autonomously learned that symbolic representation. Okay. There we go. It goes back and picks up the object, and then it takes it to the cupboard and it closes it, and it cleans up because I asked it to do that too. Okay. The delays here are computer vision because I'm bad at that. The actual planning time for a complete policy was 4 milliseconds. Okay. Since that time, we've implemented the system in 12 different settings. I think 6 of them are real robots, including Barrett, who spoke earlier's PhD thesis. Thanks, Barrett, that was great work. And it's gotten fairly solid. What we're frustrated with at the moment is how expensive it is to learn those symbols. So if you looked at that robot video, it took about 160 action executions, which is about 2.5 hours of robot execution to learn, that the cupboard needs to be open before you can grab the thing in the cupboard, right? So on the one hand, that's impressive because the robot knows nothing about physics or geometry or anything like that. It's learning that from pixels. On the other hand, if you shifted that cupboard 2 centimeters to the right, you would need to relearn that whole thing because it's all just done in a single MDP. So our main focus has been like, okay, how do we make this practical? How do we make it deployable on real robots in minutes, not hours, for a new task? And so we've taken 4 directions here that I will talk about. One of them is we focused on how you might learn portable representations. Okay, so how those representations might be reused in different environments. So instead of thinking about the original environment as one decision process, we're going to structure it, and we're going to learn symbolic representations of only portions of that structure. The other one is that we're going to exploit the fact that we have really good navigation planners and really good things like SLAM to be able to resolve the navigation portions of that hierarchy. And then we're going to construct manipulation skills that are composable by design. And finally, I'm going to talk to you a little bit about how we actually think there's a third level that needs to go on top of this. So just to talk about skill portability, here are 4 instances where we thought about them, that one of which was about hierarchies, another one of which was parameterized skills that aren't black box. 10 minutes, okay. That was Barrett's thesis. I'm going to mostly talk about this one over here. So we thought about agent-centric transfer, where you learn symbols kind of in the agent's immediate point of view, and then object-centric transfer, where you learn symbols that are a function of a particular object directly. Okay. And the object-centric symbols one is really naturally applicable to robotics, because if you look at these representations, you'll find that, well, there's something to do with the robot, and then there's something to do with the object it's facing. And you should be able to pull that out of the scene. It's very easy. We have good object segmenters now, and learn it only as a function of that object. And then whenever that object reappears in the world, you should be able to just reuse that symbolic representation from scratch. Once you've learned to open a door, you should know how to open all the doors. Okay. So this paper came out in 2022 after years of wrangling with reviewers. My former PhD student Steve James was the first author. And one exciting result from that, this is a little hard to see because it's dark, is in Minecraft. So we have learned a PDDL representation from pixels in Minecraft, an object-centric one that allows us to form complex plans like this. This is a Minecraft agent that's been asked to produce a golden clock, which involves navigating through some space and picking up some objects. And then using a forge and a hammer and other Minecraft things I don't completely understand. But the point is that once Minecraft is in PDDL, which we're able to do from pixels, then we're able to treat it as a classical planning problem, which is what it is, a combinatorial object-centric classical planning problem. And we're able to make very long horizon plans, much longer, that can be achieved using the deep network hammer and all the training data on the internet. Because it is a combinatorial planning problem. So then we thought, okay, it makes a lot of sense to think about breaking the robot's world up into objects and space. And objects are things that you manipulate, and space is just something that you move through. So let's think about learning manipulation skills that are object-centric, learning symbols that are object-centric for those, that include TAMP, and then let's think about the navigation that supports those. And what we found when we thought about this quite deeply is that we have these really good navigation tools like SLAM and path planning and intelligent exploration, and actually they're sufficient to autonomously generate. If you're given a couple of object-centric manipulation skills, we can autonomously generate in minutes the navigation stack all the way from pixels to symbols that supports planning with those manipulation skills. Okay, so the resulting paper is called Action-Oriented Semantic Maps. It's coming out this year at ICLR. No, Coral actually. It's Coral, not ICLR. From my former PhD student, Eric Rosen. An action-oriented semantic map turns out to be the mathematically required data structure for generating the navigation queries to a motion planner at the navigation level to be able to support manipulation plans. So the idea here is that we're going to assume that we have portable object-centric manipulation skills, and that those can be reused on new instances. And we're going to assume that the preconditions can be factored into two independent distributions. Now this involves a little bit of weirdness here. We're going to say that there's stuff to do with the object's logical preconditions, and then there's stuff to do with the spatial preconditions. And then we're going to say, you know what, the precondition, or the distribution is the multiplication of those two distributions. Now, it's not the multiplication of those two distributions, right? If it was, we wouldn't need to do TAMP. What it is that there are actually constraints between where exactly you stand and how exactly you can manipulate the object that depend on the things around the object. Okay, so this is an optimistic assumption, but what it does is it generates a symbolic representation we can plan with, and it generates a distribution we can sample from to use as a streamer for task and you know, in like PDL stream setting, where we can kind of generate samples, and then we can see if we can motion plan between specific points. And then we assume we have a path planner at the kind of on the map that we can just run samples through. And so it turns out that you can take a robot, just drive it through a space, recognize all the objects, drop down the spatial preconditions, take your object-centric preconditions and complete them, and then you can get a plannable representation like this one. This is a spot making a cup of coffee. What's interesting here is that the skills to make the cup of coffee were programmed in a completely different place and were tested in a different place, and we've just driven the spot through this map. It's built the action-oriented semantic map, it's completed the navigation stack, and it's able to do navigation planning to support the manipulation plan that comes out of the object-level preconditions. Okay, so it's still expensive to learn manipulation skills, it's still expensive to learn the symbols around those manipulation skills, but now they're reusable, and we can apply them to a new map in just a couple of minutes. Two things I wanted to talk about very briefly beyond that. So what we're now going to focus on is how we can learn object-centric manipulation skills that support the last little bit of motion planning that you need to do when you're standing in front of the object and there's a little bit of clutter. That still needs to be complete. But the other question is, like those manipulation skills, how do we make those suitable for integration in this kind of setting? And so what we've done is we've designed a class of manipulation skills called composable interaction primitives that have this property which we call these a head and a tail. These are motion planners. There's a structured policy, which is learned using deep learning. It's structured to be safe, to not rip the robot's hands off, to not damage the thing it's interacting with. But it has a head, which is a motion planner, which generates places you can make contact to be able to run the skill, and a tail, which gets you back out of contact. And these things are zero-shot composable because the head and the tail just, the place you get out of contact is the contact position for the next one. And so we can learn motors. First of all, it turns out that when you add the structure, as you add pieces of the structure, you get more and more and more efficient, and you can learn these skills in fewer and fewer and fewer experiences. We're down to the low tens. And then you can zero-shot compose them. So here is an example of a skill that's used to learn to open a cupboard door. So this is the kind of neural network running to open the door. You finished opening the door, and now you run a motion planner that takes you into the head of opening the cupboard inside the door. And that happens zero-shot by composition, as long as, even if things aren't reachable, actually, as long as the logical preconditions of the object are resolved, like things not locked, you can zero-shot compose them by interposing motion planning, which we're very excited about, right? If you specialize your motor controllers that you're naming in this way, then you have a very high probability of being able to sequence them. Last thing I want to talk about, my postdoc, David Paulus, is in the audience. He's on the job market, so you should all go talk to him. David, raise your hand. There he is. Okay, good. So what I think David realized in his thesis, which I really enjoyed, which is why I hired him as a postdoc, is everyone at this workshop is talking about at the low level there's motion planning or control, and then there's a level above that, and that's task planning. And now we're starting to think, or at least in our lab, based on David's work, we're starting to think actually we need one more level on top of that. Actually, it's not a two-level thing. Actually, there needs to be an object-level planning. Because we've seen in the last couple of talks, Jeanette had something about this in her talk, and several other people did as well. People are starting to want to do things like pull in language and pull in knowledge off the internet. But we don't ever talk about the things that have to be in a task-level plan. When you or I give each other a description of how to do a task, we never say, grab the thing with your left hand as long as your left hand is empty. But if your left hand isn't empty, then you can't grab the thing with your left hand. Right? We never actually discuss our own bodies. We mostly talk about what happens to the objects in the scene without reference to how those things happen. And that's the reason why recipes work. Recipes are constructed in one kitchen using one set of equipment, and they work in a wholly different kitchen on the other side of the world with different equipment because we just describe what happens to the ingredients. Okay, like, water is boiled. You can boil that any way you like, and you can boil it with your left hand or your right hand, and you don't have to be standing in front of the same object or be in the same pose. You just talk about what happens to those objects. Okay, so we think at that level, we want an object-level planner that goes one level up and initializes the task planner. And there's a bunch of good reasons why you might want this to happen. There's portability, which I just talked about. Like, it is a miracle that recipes work in different kitchens, but that's because they're at the object level and not at the task level. There's language. Language is at the object level, not at the task level. We never talk about the fact that you needed to walk up to the object to be able to pick it up, or that your hand needed to be empty. That just doesn't occur, and that needs to be in your PDDL task level, but it's weird to talk about it in language. Okay, so all the information coming at the language is going to be at the object level, not the task level. And it turns out that David has shown that you can do much more efficient planning at that level and use it to initialize the level down. So you should check out his work. His language that he developed in his thesis called Functional Object-Oriented Networks was one of the first object-level planning languages. And I think actually that's going to be really important as we start to pull in these foundation models. They're mostly at the object level. They're mostly not at the task level. And if we're going to ground these things, we should be thinking about one level up. Okay, that's all I have. Almost on time. Thank you. I've got like 2 minutes for questions. Or
Yeah. Does anyone have a quick question? Because we're a little bit over time. Please come to the mic. Ethan, you can sit.
Yes, I was curious when you were talking about object level planning. Would you consider that also with the context in which, say, a task is given, or you get one of those recipes? Say, make me a cake, but if you don't have an oven, for sake, well, now you're using a fire or something along those lines, or something more drastic, whether or not it actually gets you to the end goal or not. Is that future work or something?
Yeah, so what we can do at the moment is we can take the sequence of subgoals that an object and then drop that into PDL, and then PDL sort of figure out how to use it. And sometimes that's hard, and sometimes it's easy. What I'm very excited about is, you mentioned context. Because objects are semantic in a way that PDL aren't necessarily. We can think about it as well. You can ask the language model, what are the ways that you want this thing? And actually it can give you back semantic useful information. And then it'll help you kind of scope the box, right, decide what you want. So I think there's a lot of power there. We just began to think about what that might look like. That's not very much your question. Just that overall summary can be thought of as lots of cool things to think about, and we have thought of some.
Thank you.
Does that work?
Yeah, thank you.
Right, let's thank George again.